This lecture covers eclipses, one of the details that I skipped over earlier when describing the lunar phases. Okay, so I once again have my light bulb here to represent the sun. Here's my styrofoam ball to represent the earth. We're going to think of the plane of the disk as the ecliptic, the plane of the earth's orbit about the sun. And then I have my wooden ball here, for example, to represent the moon. Now, earlier when talking about lunar phases, we described new and full moon. So first of all, new moon. So the moon is positioned here like so during new moon, such that if you were standing here on the surface of the earth looking at the moon, you would see the entire disk of the moon in darkness. You're looking at the night side of the moon. However, if the moon lies directly between the sun and the earth like so, the shadow that is cast by the moon then lies on the surface of the earth. So if you were standing here within the shadow, you would then see what is called a solar eclipse. So a solar eclipse occurs during new moon when the moon is in between the sun and the earth. Okay, now 2 weeks later, let's say it's full moon, like so. So if you're standing here on the surface of the earth and you then look towards the moon, you see the entire day side of the moon, therefore the moon is full. However, if the moon falls into the shadow that is cast by the earth, this then means that if you are on the night side of the earth looking towards the moon, you would then see what is called a lunar eclipse. So a lunar eclipse occurs during full moon. Now we have a new moon and we have a full moon each month. Why don't we have 2 eclipses every month? The reason for that has to do with the fact that the moon's orbit about the earth is on an angle. It's angled about 5 degrees or so with respect to the plane of the ecliptic, the plane of the earth's orbit around the sun. So then therefore picture that in the following way. So I'm going to take my moon here and I'm kind of orbit it on an angle with respect to the disk like so. So it kind of goes like down below the disk, kind of above the disk like this. However, every once in a while, approximately once every 6 months or so, the geometry is just right such that the following can happen. So the moon is orbiting the earth and the earth is orbiting the sun, and then all of a sudden, boom, the geometry is just right to have a lunar eclipse, for example, or to have a solar eclipse like so. These eclipse seasons, as they're referred to as, occur approximately once every 6 months or so as the moon orbits the earth and as the earth orbits the sun. Okay, next what I'm going to do is draw out on the board for us the geometry associated with 3 types of eclipses, not just the solar eclipse and the lunar eclipse, but also a type of solar eclipse called an annular eclipse. As I draw out these situations, the geometry associated with them, we'll then understand why it is we see what we do with the individual eclipses. Okay, so first of all, let me begin by drawing out the geometry associated with a lunar eclipse, which occurs during full moon. As I draw out that geometry here, keep in mind that definitely this is all not to scale. Okay, so we have a lunar eclipse, which occurs during full moon. Okay, here's the geometry behind that eclipse. Okay, so first of all, let's say that right here is the sun. Okay, right here is the earth. And now here's the geometry of the shadow that is cast by the earth. So imagine first of all sunlight coming from the top of the sun and passing by the top of the earth, like so. And then imagine sunlight coming from the bottom of the sun and passing by the bottom of the earth, like so. And then what you end up with here in 3 dimensions is a cone-shaped shadow that's referred to as the umbra. However, there are 2 other less distinct shadows to the side. These are referred to as the penumbra, and they are formed in the following way. So imagine sunlight from the top of the sun passing by the bottom of the earth, like so. And then sunlight from the bottom of the sun passing by the top of the earth, like so. And then here and here, you end up with these less distinct shadows that are referred to as the penumbra, like so. They're less distinct for the following reason. Imagine, for example, being right here in the penumbra. Can you see the bottom of the sun? Yes. However, can you see the top of the sun? No, because the earth is in the way like so. So you end up with these less distinct shadows, the penumbra, for that reason. Okay, now all of what I'm about to describe here occurs over the course of just a couple of hours during full moon. That is, during the lunar eclipse itself. As I draw this, however, keep in mind once again that this is not to scale. So the eclipse begins when the moon is here, like so. Once again, this is all during full moon. This is not a gibbous phase. The eclipse begins like so, as the moon then begins to pass into the penumbra. As it passes into the penumbra, you're really not going to notice much difference in the moon's appearance from the surface of the earth. The reason for that is because sunlight is still striking the moon, so it's going to look like full moon, but as the moon gets deeper and deeper into the penumbra, you'll begin to notice some subtle changes. Number one, the moon will get a little bit dimmer as it gets closer and closer to the umbra. In addition to that, you're going to begin to notice that the moon takes on a definite three-dimensional appearance. This is usually not what you see, however, during ordinary full moon. During ordinary full moon, sunlight is just striking the moon face on and is then therefore reflecting back to you, and basically the moon looks completely flat. It looks like a two-dimensional disk in the sky. However, during the penumbral phase of the eclipse, the sunlight that is striking the moon is coming in somewhat from the side. So because of this then causes the moon to take on a definite three-dimensional appearance. It looks like a little spherical golf ball in the sky, for example, that you can say reach up and grab. Okay, and then the moon starts to pass into the umbra. As it starts to pass into the umbra, it starts to look like it goes through phases. That is, it'll appear first of all as full, and then it starts to sort of look like a gibbous, sort of look like a quarter, sort of look like a crescent, and so on, as the moon then begins to pass into the umbra. All of this occurs, however, over the course of only about a half hour or so. You'll be able to see this in some of the pictures that I reference in a screencast that follows this lecture. But then after that, the moon passes within the umbra. When it passes within the umbra, it takes on a reddish color. And the reason for that is because what you're actually looking at is sunlight that is passing through the Earth's atmosphere here and here. That sunlight is refracted a little bit. This means that it's bent by the Earth's atmosphere such that it strikes the moon. It reflects off the moon, then to your eye. So when you look at the moon during a lunar eclipse and it takes on this reddish color, the reason for that is because you're basically looking at the world's combined sunrises and sunsets. You'll see this in the photographs in the screencast. And then the whole thing happens in reverse. The moon begins to emerge from the umbra out the other side, sort of looks like it goes through phases, like it sort of looks like a crescent, a quarter, a gibbous, and so on. And then you have the penumbral phase once again, and then after that, the moon eventually passes out of the penumbra and the eclipse is over. Total amount of time from one side of the diagram to the other is a couple of hours. Notice that everybody on the night side of the Earth will be able to see the lunar eclipse. So because of this, it seems like lunar eclipses are more common than solar eclipses, but they're not. They actually occur at about the same frequency as solar eclipses do. It's just that a large portion of the Earth can see the lunar eclipse. You just basically have to be on the night side of the Earth in order to be able to see it. Okay, that's the lunar eclipse. Let me now take you through the solar eclipse. The solar eclipse is the big show, if you will, when it comes to eclipses. Okay, so now we have the solar eclipse. This occurs during new moon. And once again, we take a look at the shadow's geometry. So I'm going to draw the umbra and penumbra once again, but in this case, it's the moon that's casting the shadow. This is all during, once again, new moon. So let's set it out to scale. Right here is the sun. Right here is the moon. Okay, and then we first of all form the umbra in the following way. We have sunlight coming from the top of the sun, passing by the top of the moon like so. Sunlight from the bottom of the sun passing by the bottom of the moon like so. There's the umbra. And then the penumbra is formed in the following way. Sunlight from the top of the sun passing by the bottom of the moon like so. And then sunlight from the bottom of the sun passing by the top of the moon like so. And then where is the Earth in all of this? Once again, this is definitely not the scale. Here's the surface of the Earth. Like so. So let's say, for example, that you happen to be standing right here. You're standing in the penumbra. What do you see? You see what is called a partial solar eclipse. So if you were standing right here, notice that you would be able to see the top of the sun. However, you would not be able to see the bottom of the sun because the moon is in the way. You would then therefore see what is called a partial solar eclipse. The moon has to be covering up more than 99% of the sun for you to actually be able to safely look at it with unprotected vision. So during a partial solar eclipse, never look directly at the sun for this reason. You will damage your eyesight if you do. However, there are various ways to safely observe the partial phase of the solar eclipse. Now let's say that you happen to be one of the lucky ones. You're standing right here in what is referred to as the path of totality. What is it that you're going to see? Well, first of all, the reason why the total solar eclipse is so spectacular is because of a very simple cosmic coincidence. That coincidence is as follows. Take a look, for example, at the moon's disk in the sky, and you'll see that it subtends an angle in the sky. That angle is about a half a degree. In other words, the apparent size of the sun and moon in the sky is a half a degree. They're actually the same. This is just a coincidence. So then therefore, during a total solar eclipse, the moon's disk just barely covers up the sun, resulting then in all of the spectacular effects associated with the total solar eclipse. I have seen 3 total solar eclipses in my lifetime. I hope to see a couple of more in the next couple of decades. Make sure that you see a total solar eclipse sometime in your life. It is one of the most fantastic sights in nature. So then what actually happens if you're standing here in the path of totality as the umbra then begins to approach your location? Well, what you're going to see first of all is that it just kind of looks like normal daylight as the partial phase occurs. But if you look carefully at the color of the sky, especially near the sun, you're going to see that the sky gets darker and darker and almost takes on a purplish cast, for example, as totality approaches, as the moon is covering up more and more of the sun. The sun is still too bright to look at with unprotected vision, but definitely things begin to look different as the partial phase occurs. And then you look towards the west. When you look towards the west, you'll notice that it's much darker in that direction than it is towards the east. And the reason why is because the umbra is approaching. You can actually see a cone-shaped shadow extending out of the sky, and it's rushing at you at a speed of about 1,000 miles per hour or so. You really start to get this strange feeling that something weird is about to happen, and you have no control over it whatsoever. And then, right at the moment of totality, the umbra then reaches your location. And all of a sudden, it's as if you go through sunset and twilight in just a couple of seconds, as opposed to the course of 45 minutes. The sky all of a sudden gets really dark. And then, yes, you could safely look at the sun when the moon is completely covering it. You're going to be able to see the sun's corona, the outer atmosphere of the sun around the sun and the moon. And you can also see the bright stars and the planets Mercury and Venus right next to the sun. The size of the umbra, however, on the surface of the Earth is small. It's less than 100 miles wide, and it's racing across the surface of the Earth at a speed of roughly 1,000 miles per hour. So for this reason, only a small portion of the Earth's surface can see the total solar eclipse, and the amount of time necessary for you to see the eclipse is only a couple of minutes. So during a total solar eclipse, it's almost as if all these different things start to happen very quickly and happen at once. Once again, I reference all of these effects and I show you pictures of these effects in my screencast on eclipses. As I've already mentioned, make sure that you see a total solar eclipse sometime during your lifetime. It is an unbelievable, spectacular event. Okay, next there is a third type of an eclipse, and this third type of an eclipse is very similar to a solar eclipse, so it occurs during new moon, but it's referred to as an annular eclipse. Let me take you through that. Okay, an annular eclipse, as I just mentioned, also occurs during new moon. The moon's orbit about the Earth is not a perfect circle. It's an ellipse. So because of this, the moon is a little bit further away in its orbit than it is at other times. If it just so happens that it's new moon and the geometry is just right for a solar eclipse to occur, but the moon is at its furthest point in its orbit, this then means that it looks a little bit smaller in the sky. So then therefore the moon is not going to be able to quite cover up the sun's disk. Instead, you see a ring of sunlight. The mathematical word for ring is annulus, and that's why this is referred to as an annular eclipse. So here's what the sun would look like in the sky at full annularity. So right here is the moon's disk like so. I've drawn it smaller than the sun, so it doesn't quite cover up the sun. So because it doesn't quite cover up the sun and you end up with this annulus of sunlight, here's how you spell that word, by the way, you don't get all of the spectacular effects as you do during a total solar eclipse. The sun is still too bright to look at with unprotected vision during full annularity. Okay, now the difference on the geometrical diagram that I'm about to draw between the solar eclipse and the annular eclipse is as follows. The moon is further away from the Earth in its orbit. The easiest way for me to draw that very simply is just to do this. Okay, so now I'm going to extend the umbra like so, and the penumbra like so, and then I'll go ahead and position the surface of the Earth like this. Like so. So notice that the moon is a little bit further away from the Earth on this diagram than it was on the previous diagram for just the ordinary total solar eclipse. This crossing over point right here of the umbral shadow is above the surface of the Earth. It's in the Earth's atmosphere. So then therefore, if you were standing here in what is called the path of annularity, then you would see the annular eclipse as such. So that's the basic geometry of the annular eclipse. It's once again very similar to a solar eclipse. It's just that the moon is a little bit further away in its orbit. Make sure, once again, that you watch the screencast that accompanies this lecture on eclipses, where I show you photographs of the individual eclipses themselves. But when it comes to eclipses, photographs and my descriptions, quite frankly, don't do it justice. You really have to see it for yourself, especially with respect to the total solar eclipse. That concludes this lecture on eclipses.